Hello and welcome everybody. Today we're going to continue our talk of different functions. We're going to look at linear, quadratic, and exponential functions. These are all things that we actually have done before. We're just going to look at them in further detail. So just to start, I have a couple pictures up here. And if I asked you which picture represented the linear function, I hope you would say that this airplane does, because it's going in a nice straight line. So when we're talking about linear functions, we're talking about lines. And if I asked you which function you thought I was trying to represent with the McDonald's sign, I hope you would say, well, a quadratic function, because it has that nice U shape or that nice parabola in both of those arches. So again, this would represent a quadratic function. And then the third and final one, right, as we see it never crosses the x-axis, and as we're going from left to right, it starts getting really big, really fast. So hopefully you should say, well, that looks like an exponential function. More specifically, we could even say that it's exponential growth. What we are going to do today is we're going to determine if a function is linear, quadratic, or exponential by looking at an equation, looking at a graph, and looking at a table. Oops, I need to get it to switch. There we go. All right, so looking at this first one, again, we're going to be able to look at data to determine if it's linear, quadratic, or exponential. And eventually here, we're going to get to tables like we see here, and we'll be able to look at and determine which one it is, but we are not quite there yet. So first off, just as review, looking at the different equations that we have, the first one being linear. Linear functions were one of the first things we worked with in terms of functions. That's where we spent 20-some days doing that graphing challenge. Just a little refresher on that linear equation. Y equals mx. M, remember, represents our slope, and b represents our y-intercept. Again, linear functions make a nice straight line. Quadratic functions, those are the ones that we should be most familiar with. That's the one we just spent the last probably month and a half on. Y equals ax squared plus bx plus c. This particular quadratic is in standard form. Remember, they make that nice U shape. Unless this a is like negative, then it would be flipped. Again, that nice U shape on that quadratic function. Nice parabola. Exponential functions, on the other hand, it's been a while since we've done these two, are in this form. Y equals a times b to the x. If you recall, a represents our initial value. Or another word for initial value is just our y-intercept again, our starting value. And b represents our growth or decay factor. Growth / decay factor. If you recall, we have exponential growth and we have exponential decay. We know it's growth. If our b value is bigger than 1, we have growth, which must be the case with this skateboard ramp here. As I go from left to right, it gets bigger. However, if b is less than 1, then we have exponential decay. So that would mean if I was going from left to right, it would start up high and then it would get really small. Those y values would. So those are the types of equations. Again, the dead giveaway that it's a quadratic function, if I just give you an equation, should be, well, there's a squared there, x squared. That's quadratic, degree 2. Exponential gives away if x is an exponent, right here. And then linear, we should be pretty familiar with if it's in that form, y equals mx plus b. So let's go ahead and do some graphing to determine what type of model to use. It says graph the data, determine what type of model would be best appropriate. So a lot of things in life are not perfectly linear, not perfectly quadratic, not perfectly exponential, and we've talked about that before, but we can use a model that best fits our data, right? It best represents it so it can allow us to estimate and predict different values. So for this particular example, we are just going to plot points and determine, does it look most like a line, most like a parabola, or most like that exponential function. So we're just plotting points. So the first point I see is 1, 3. X value is 1, y is 3. We get 0, 0. Negative 3, 3. Negative 1, negative 1. And negative 2, 0. If we look at this and we connect our points, should be saying, oh, that looks like a U or a nice parabola. So that'd be best modeled by a quadratic function. Quadratic function. We did that yesterday, right? We could generate an equation for that using quadratic regression on our graphing calculators. Same thing for the second one. We're going to go ahead and plot points. So I'm going to start by plotting the point 0, 2, which is right here. Negative 1, 4. 1, 1. 2.5. Right? It doesn't look like a U. And it doesn't look like a straight line. And this looks like a nice exponential function. Nice exponential function, because as I'm going from left to right, I'm getting really small. I can actually say, well, it's exponential, and more specifically, I can also say that it represents decay. Then finally, the last one, just again, plotting some points, just practicing doing that. We got negative 1, negative 2, 0, negative 1, 1, 0, and 3, 2. I connect those points. Looks like a beautiful line. So it tells me I'm looking at a linear function. Again, just by looking at the shape of what we get when we graph, we can determine what type of function we are looking at. We can also determine what type of model to use or what type of function to use just by looking at a table. So, when you do this, the x values in the table must have a common difference. What that means is they have to go up by the same amount. So if I made this table over here off to the left-hand side, if I did my x values being 1, 2, 3, 4, this would be okay, because my common difference, I'm just going up by 1 each time. 1 to 2 is up 1, 2 to 3 is up 1, 3 to 4 is up 1. They have a common difference. Whereas if I made a table over here, did x, y, let's say I went 1 to 2, 2 to 3, and then I went to 7, this would not be okay because I don't have a common difference with my x values, right? I go +1, +1, but then all of a sudden I go +4. I make a big jump there. So those do not have a common difference. So that'd be, I can't use that table then to figure out what type of model best models it. Or I'd have to do a little bit more work with that particular table if that was the case. So let's first start talking about linear functions. And we've actually, like I said, talked about this before, so this should feel a little bit like a review. We use a linear model to model data when there is a common, we say a common difference between the y values. Meaning I add or subtract, common difference means add or subtract, by the same amount each time. So if I look at I'm going to say add or subtract the same number, so we have a little bit more notes here. So if I look at my table over here, I'd first check my x values, and I have a common difference there, so that's good. I can use this table exactly how I see it. I don't have to worry about anything, because I'm just adding one each time. I come over here and I look at my y values, and I think, how do I get from -1 to 2? Looks like I'm adding 3. How do I get from 2 to 5? Looks like I'm adding 3. 5 to 8, looks like I'm adding 3. Since I'm adding by the same amount each time, that means I have the same common difference, which means I'm looking at a linear function. Or it will best be modeled by a linear model. So after we determine it's linear just by looking at the table, we can also write an equation. In slope-intercept form, y equals mx plus b. My slope is just my common difference, what I'm changing by each time. So here my slope would be a positive 3, so I have y equals 3x plus my y-intercept. And if we recall the definition of a y-intercept, it's where it crosses my y-axis. So that means my x value has to be 0. So when x is 0, y is 5, so my y-intercept is 5. So here is my equation. Y equals 3x plus 5. Next, now, we're going to go ahead and talk about an quadratic, I guess is next, quadratic model. So we use a quadratic model to model data when the second differences between the y values are equal. So again, we look at our x values. We have a nice common difference between all of them, just adding 1 each time. For a quadratic function, we might first start by checking if it's linear. That's always the one I check for first. So I look from 1 to negative 1, I subtract 2, negative 1 to 1. Oh no, I'm adding 2 now. 1 to 7, I add 6, 7 to 17, I add 10. Clearly that's not linear because the common differences are not the same between those terms. However, with quadratic functions, which I just said here, we have to look at the second differences. So I look at the differences between the differences. So if I check here to get from negative 2 to 2, I have to add 4. 2 to 6, I have to add 4. 6 to 10, I have to add 4. Since my second differences are the same, that means that this can be best modeled by a quadratic function. And because those second differences are the same. Quadratic functions are a little bit harder. Unlike linear ones, we can't just make an equation right away. But in order to make an equation, we would have to use quadratic regression like we did yesterday. On the calculator. Maybe I'll even add your graphing calculator. So if you don't have a graphing calculator like you won't on the homework today, you won't have to write an equation for a table that models a quadratic function. On the tests and things, you will have to because we'll have our graphing calculators then. So we have one more form to talk about. So what I'm going to have happen now is the sub's going to change the second video. And then we'll finish with exponential. We'll do a little practice. And then you get some time to practice on your homework.